Hello, everyone. I'm Jaeha Kim with Scientific Analog. This is a post-recording of a talk that I gave at DVCon Europe 2024, and it was titled a UVM Testbench for checking the global convergence of analog mixed signal systems. So this talk is about global convergent failure that can happen in analog mixed signal system. If your analog mixed signal system is a nonlinear system, it might have multiple stable equilibrium states. In other words, when you run the system for a long enough time, it will eventually settle into a steady state, but there are multiple possibilities. For example, in this diagram, we have two equilibrium, EQ1 and EQ2. It means that depending on where you start from, in other words, depending on the initial state, the system may settle into a different final state. For example, if you start from state A, it will converge to a stable equilibrium EQ1. If you start from a different initial state, B, then it can converge to EQ2. If one of these equilibrium state is a wrong state, some undesirable forbidden state, then you have a global convergence failure because depending on how you start the system, your system may work or not. So this can happen in nonlinear system. And for traditional analog circuits, these global convergence failure happen only for some limited set of circuits, such as bandgap references with self-biasing schemes. They have some startup failures, and also some oscillators, which may exhibit multiple mode of frequencies. But today, we now see more frequent occurrences of these failures due to the use of digital calibration loops calibrating various aspects of the analog circuits. This happens because once you bring in the digital calibration loops, digital circuits are inherently nonlinear, and those nonlinearity turn the entire system into a nonlinear system, which are prone to these kinds of failures. The example that we're going to use in this talk is called adaptive decision feedback equalizer. So to understand the circuit, you need to have some background in wireline communication. In wireline communication, you have a transmitter transmitting a series of digital bits through a channel in order to communicate with the receiver on the other side. Now, this channel may have some frequency-dependent loss. For example, it may attenuate a high-frequency signal while having a reasonable gain for the low-frequency signal. That means even when you send a 1-bit pulse, representing a bit 1, that the energy of that 1 bit can be spread into the adjacent bit, such as like this. Okay, so these energy that got spread into the adjacent bit periods are basically interference, and these are called inter-symbol interference, ISI. Okay, so in wireline communication, people use multiple kinds of circuit called equalizer. They try to compensate these frequency-dependent loss effects of the channel or the ISI. For example, you see a CTLE, which stands for continuous time linear equalizer, that try to apply the linear filter that has the opposite frequency-dependent characteristics to the channel loss so that the channel gain more or less become constant across the frequency. When that is not enough, people use another type of equalizer called decision feedback equalizer. And what it tries to do is it tries to reconstruct the ISI that comes after the main signal bit, which is called post-cursor ISI, based on the previous bits that this receiver has detected, and using a FIR filter. Of course, this is assuming that this DFE knows about the channel characteristics, and by applying the proper filter coefficient values, W1 through W4 in this example, and multiply each of them to the corresponding previous bit, add them up, and in constructing the post-cursor ISI, expecting for the current bit. Then you subtract that from the incoming bit, and now you have a signal that is ISI free. More precisely, post-cursor ISI free. We call that an equalized signal. Of course, when you use these wireline communication circuit in the field, there's no way you can predict the channel characteristics because people can connect using different channels that you don't know, in advance of time. So most decision feedback equalizer or most equalizer, they employ a adaptation controller, which are typically done in digital circuits. And they can, calibrate this filter coefficient either during the startup in the foreground or during the normal operation in the background. But what they basically do is they take certain observation from the receiver. For example, the output of the data slicer, we call data. And the another output we call errors, which is the comparison result of those equalized signal against the different threshold. For example, the threshold where you expect that the level 1 is expected to be, and the threshold, the data level that where do you expect the level logic 0 is expected to be. Okay, based on those information, it will incrementally adjust these coefficient value so that the post-cursor ISI predicted by the DFE is, optimal. For carrying out this adaptation, perhaps the most popular algorithm being used today is called sign-sign LMS adaptation algorithm. LMS stands for least mean squares algorithm, which is a really old technique and also very powerful that adjusts the coefficients in the adaptive filter in a direction that can reduce the mean squared error. So here we have the mean squared error, which is computed by, let's say you have a DFE on the right-hand side. You have an incoming input we call Y of N. Now we call the output of the DFE as the Y sub EQ, the equalized signal. And then what we're expecting here is a binary signal that having ones and zeros. Okay, so for each of the logic level, we do have a expected or desired level. So compare the two. If there's any remaining error, well, that's an error. Okay, so the adaptation engine observes that error and uses this algorithm to adjust the filter coefficient in a direction to reduce it. In this setting, the derivative of the error square can be simply expressed as a product between the current error and the input that arrived k bits earlier, y of n minus k. And the sign-sign LMS algorithm simplifies it in order to reduce the required hardware. In other words, it only detects the polarity of this derivative so that it will just adjust the filter coefficient in the right direction. And for the magnitude, it will just use a fixed step. And in that setting, to detect the correct polarity of this direction, we just need to know the polarity of the error and the polarity of the y of n minus k. The polarity of the error is what I refer to as the error information in the previous slide. So we are comparing the equalized signal to the expected level, DLEV1 and DLEV0, which corresponds to the data level for logic 1 and data level for logic 0, respectively. And depending on which one's higher, you get the error signal that indicates you're too high or too low. Okay. And the other information that we need is the polarity of y of n minus k. Note that this is actually the input to the DFE. But in most implementation of the sign-sign LMS algorithm, they approximate this information with the other information, which is the polarity of the output of the DFE, y sub EQ of n minus k. And the reason is that's already available. That's basically the data output of this receiver, which you already have if you're building a receiver. So in order to eliminate the need of adding another slicer, detects the polarity of the unequalized input, you just use the output of the data slicer you have. And it turns out it is this approximation that can cause various kinds of global convergence issue in this adaptive DFE. Especially if there is a large difference between the y of n and y sub EQ of n. For example, when you have a large ISI in the channel, so that the filter coefficient W1 through W4 has to be large in order to compensate it, then it is more likely to have the global convergence issue. So the goal of this work is to present a UVM test bench that can check the global convergence property of a sine-sine LMS adaptation loop for this DFE. So we are trying to answer a question: does the loop always converge to the same final state, regardless of the initial state? For various reasons, DFE, the adaptation engine, can be initialized to various starting condition. For example, you can initialize your coefficient value, or maybe it will start recalibration in the middle. And we don't want our DFE to settle to some bad state and never get out of there, because that will be a global convergence failure. And in order to achieve this, we need to address two problems. First, well, the UVM test bench works within SystemVerilog. It means we need to be able to model a wireline receiver, including the DFE, in SystemVerilog. And our UVM test bench should be able to test all possible initial states and check whether the system will all converge to the same final state, starting from each and every initial state. That sounds like a very exhaustive work. So for the first problem, modeling a high-speed wireline receiver in SystemVerilog, let's see what is needed. What you're seeing in this slide is a typical configuration of a wireline transceiver. So on the transmitter side, you have a circuit called phase lock loop that generates a precise clock that can trigger the transmitter. This allows the transmitter to transmit each bit at a precise time interval. Now the transmitter usually just converts the digital data into an analog signal, like ones and zeros, but it may have additional capability of pre-equalizing the signal, for example, emphasizing some high-frequency component of the signal. In that case, the signal may not look the pure digital. Now our model should include the frequency-dependent loss characteristic of the transmission line channels, and there may be some unwanted reflection if you do not terminate them properly. Now on the receive side, as I said, people typically use a linear equalizer first to tame the ISI, and then they use a combination of a data receiver and the clock and data recovery loop that first recovers a clock to sample the data, and then recovers the digital information, ones and zeros. And in this position, we will use a DFE, the one that I explained before, which can be adapted continuously using the LMS architecture. So this slide kind of demonstrates or illustrates that we need to have a capability of simulating the analog signal propagating from the transmitter, going through the transmission line channel, and going through the equalizer, and finally detected by the data receiver, including the DFE. And that analog model has to work alongside with the digital adaptation loop or some other digital control loop, all within SystemVerilog. In other words, we need a way to bring analog circuits into SystemVerilog, and we still need that analog model to work with the other parts, other digital parts. Well, if you are an XMODEL user and you know what the solution is, well, XMODEL from Scientific Analog is a plugin extension that enables your SystemVerilog simulator like PCS, Xcelium, Questa to perform a very fast and accurate analog mixed signal simulation. It has a very powerful event-driven algorithm that can deliver a much faster speed compared to a real number model. And it's very, it's easy. Has a very powerful capability of modeling both a functional and a circuit level model of the analog circuits. Yet, all the models that you can describe is fully compatible with SystemVerilog. It's still 100% pure SystemVerilog. That your model can be work in a flow which is fully compliant with the SystemVerilog flow, such as UVM. So it meets our goal. And this waveform, in case you have used the XMODEL user and you watch the tutorial, this is a very familiar slide, which illustrates that XMODEL is the ideal solution for simulating the data pulses propagating through the lossy channel and the equalizer. So on the slide, we see three waveforms. First one is the signal transmitted by generated by the transmitter. So ones and zeros. And every time the value changes, there are these events being triggered, which is, understandable. Now, when this signal propagates through the lossy channel, we get the second signal, the green line. Now, due to the frequency dependent loss characteristics in the channel, now the signal is smooth and continuous. Yet, the number of events, you see these markers where indicate the events, and their numbers are very, very few. In fact, they're only triggered when there is a corresponding event at the input. Okay, and the same is true when the signal is passed through another filter, such as the linear equalizer. You generate another analog signal, yet the number of events on that signal is very few. In fact, it's the same number as the number of events on its own input, the green one. And thanks to the functional expression used by XMODEL, we can fully express what happens between any two events. So by reducing the number of events being triggered, the simulation is very fast. And by using the functional equation, we retain the full accuracy. The XMODEL provides a set of building blocks called primitives, and you can just put them together to build what you want. And because of that, you can also do that in a schematic form. So I'm showing here is the schematic model of the decision feedback equalizer receiver, including the adaptation loop, digital adaptation controller. But this is essentially a SystemVerilog flow, listing each of the primitive as instances one by one. Here we see a variety of XMODEL primitives. For example, you see an add primitive that first computes the differential component of the input, and is also used when you try to subtract the post-cluster ISI reconstructed by the DFE. You also have compare primitive, which act as a clock comparator that samples the two analog input and detects the polarity of their difference. Some special primitives are filter disk underscore bar, which models the discrete time filter with variable coefficient, which is basically our FIR filter in the DFE. You need a set of DACs because our digital adaptation controller will produce a set of digital values that adjusts the filter coefficients, and we want to convert that to some analog value. And let's not forget about this digital adaptation controller, the Sign LMS controller. Now, since XMODEL is fully compliant with SystemVerilog, this part can be written in pure Verilog RTL and seamlessly work with the other parts of the circuit, which are analog. Now, having addressed the first problem, let's take a look at how we can build a UVM test bench that verifies the global convergence of this DFE adaptation controller. So the adaptation controller will start from a certain initial state. Here, when I say state, it's basically a collection of digital value representing the filter coefficient, W1 through W4. And over time, the adaptation controller will try to adjust it so that the post-cursor ISI reconstructed is close to an optimal. Okay, so over a certain period of time, it will keep adjusting, and eventually it will reach to a final value where the adaptation loop no longer makes further adjustment. Okay. Now our problem is we want to try every single initial state available in the system and see each and every initial state will lead to the same final state. That's what we want to do. But you can have a very large number of initial state available, especially if you have a large number of bits representing these filter coefficients. But one observation can lead to some savings in the number of trials required. That is, when you run a given trial, starting from a certain initial state, it doesn't get to the final state right away. It will have to pass through some intermediate states. Here in the diagram, S1 through S4. So that means when you run this trial run, you're not only knowing that S0 leads to S final, but also S1 through S4 also leads to the same final state, S final. In other words, we don't need to run another simulation starting from S1, S2, and so on. That will allow us to save the number of trials required to be performed. So here's an overview of the UVM Testbench that we are proposing to verify the global convergence. It has three key components: the driver agent, the fixture in the middle, and the monitor agent. The monitor agent will select one initial state to start a new trial with. Of course, that news, in order for the simulation to be efficient, you want to choose an initial state that has not been explored before. Okay. So when the driver chooses a new initial state, now the fixture will initialize the DFE adaptation loop with that value, and then let the DFE run, let the adaptation loop run. And over time, it will change, it will adapt the filter coefficient, and eventually it will converge to some final state. So all those states that are visited in the middle will get collected by the fixture as well and passed to the monitor agent. So the monitor agent, while observing the same, the traversal of these states, it will detect whether the simulation has reached the final state, or it has visited some state that has been explored before, because it means that we know the outcome from then on. Well, note that the driver agents need to pick an initial state that has not been explored before. So we need to know what state has been explored in the past. But that information is possessed by the monitor, because that's the one collecting the traversal of the states. So we need a way to pass the information from the monitor back to the driver agent. To do that, we use a coverage database, basically recording all the state that has been visited and the corresponding final state for each of this initial state. And this coverage database is shared through a UVM configuration DB. Okay, so using this shared state coverage database, the monitor will first update this database with the traverse states when each of the trials is complete. Then in the next trial, the driver agent can look up this coverage database and see which initial state has not been tried yet and pick one among them randomly. Another thing to consider is that each trial may not have the same duration because, well, depending on the initial state you start with, it may take different time to get to the final state. Or in the middle, the DFE adaptation loop will eventually get to the point that you know that has been explored before, so that you know the outcome afterwards. That means you don't have to keep running the simulation until it reaches the final state because you know the final state already. So you need a way to kind of stop the trial in the middle and the signal the driver that you can now start a new trial. Or maybe you also need to say that, oh, all the trial has been completed. Now we can just go back, we can reach the conclusion and stop the simulation. So all that says is that we need a way for a monitor to tell the driver that it's now time to start a new trial, or tell the scoreboard that conclude the simulation. For that, we use a global UVM event named locked that's shared through a UVM event pool. Okay, so the monitor signals the driver with this locked event when the state which the DFE adaptation loop reaches the state that has been previously explored, or it has reached a final lock state. So you can run a simulation, and if the DFE adaptation loop keep revisiting the same state over and over, although it's a new state, then it's considered a lock state, and then you don't have to run you don't have to run the simulation any further. Okay. Then when it's signaled, the driver agent will run a new trial. But if it has exhausted all the states available in the database, then it means that, oh, for all the states I have visited before, they all converge to the same final state, then it is a pass. Or if it has discovered that some initial leads to one final state where other initial state leads to a different final state, well, you already found the failure, and you stop right away. Okay, so when one of those conditions is met, the monitor will stop the simulation and the scoreboard will report the pass and fail. So let's look at some simulation results. First, we tried it with a channel that has a very high loss of -45 dB at the Nyquist frequency, because this is a typical situation where we see a lot of issues with the DFE adaptation loop not converging. So with this, you see a trajectory of the DFE filter coefficients. At this point, it is being initialized at some random value picked by the driver, and it is being controlled by the adaptation loop. At a certain point, like at the points indicated by this red dotted line, the filter coefficient make a sudden jump. That's when one trial is finished and the UVM Testbench is starting a new trial with a new initial state. Okay. So for the first 6 trials, the UVM Testbench found that, oh, they are all converged to the same final state. Things seems to be fine. And for the last trial, the 7th trial, it has discovered that, oh, the system is converged to a different final state to the one that has been seen before. Okay. The bottom eye diagram is just for illustrative purposes. It doesn't plot this diagram, but just to give you an idea what each of these final states correspond to. The final state, the reached by the first 6 trials are the correct final state. That gives you, although small, but some eye-opening, so that you can tell the difference between 1 and 0. On the other hand, the other final state reached by the last trial is wrong state, because it does not give you any separation between ones and zero. So if you do the communication in the state, well, you cannot do a proper communication. So the point here is that if your system has a global convergence failure, the UVM testbench is able to find it pretty soon with very small number of trials. So now we try to lower the loss in the channel, let's say down to minus 20 dB per decade. And then we found that the adaptation loops still have a global conversion issues. So with no other constraint on the filter coefficient, other than that, it has a bounded range. We were able to find that the system has two final lock state it can reach. One of them is a correct state that giving you a much better eye opening, whereas the other state is kind of a wrong state. They kind of give you a limit cycle behavior around this adaptation feedback loop. Okay. So knowing there is a problem, we constrain the range of the initial value that the DFE weight can have. So for example, we constrain the sum of the absolute value of the coefficient to be less than 0.05, of course, when they're converted into an analog value. And then we force their magnitude to be in a descending order. W1 has to be greater than W2, and W2 has to be greater than W3 and W4. And with these constraints, we found that the DFE adaptation loop will have a successful global convergence, where we find that all the possible initial state will converge to the same final state, giving this clear eye opening. In order to reach that conclusion, the UVM testbench had to run 1721 trials, which is a lot of number, which took 5 hours. But it was actually a lower number than what we had to run, which was 2347. So by not running another trial on the individual states that are visited during the other trials, we were able to achieve a 26.7% reduction in the number of trials. Okay, here's a summary. So I just presented a UVM testbench that can verify the global convergence property of an analog mixed signal system, such as the adaptive DFE. So it checks whether the system reaches the same final state, regardless of the initial state value. And in order to do that, it launches a sequence of trial runs that try from a different initial state and see if they all lead to the same final state. This is essentially a reactive stimulus testbench. Like you give a stimulus, you observe the response. Depending on the outcome, you continue with a different trial that depends on that response. But its stimulus response pattern is kind of unique because for one set of value, you get a trajectory of states, whose number can be variable. And then you have some additional action that you want to take based on that trajectory. For example, updating the coverage database and making such a decision whether you go or no go. So that pattern is kind of unique, which doesn't fit into a traditional reactive stimuli testbench. So we use two things. One is a state coverage database shared through a UVM configuration database, and a global UVM event shared through a UVM event pool. Okay, so that was a nice tip to realize this testbench. All right, so that concludes the talk, and I just want to conclude this by thanking our supporters, the Samsung Electronics and the IDAC in Korea, as well as the Scientific Analog. Thank you very much.